that means, and I have a discussion, if this is a 200-gram mass, and it's at rest, that means that gravity is pulling down 2 newtons on that weight. And I ask them, what is the tension and the strain? And what do you think, if there are a 2 newton weight on this side and a 2 newton weight on this side, what's the misconception that they're going to say is the tension and the strain? 4. They're going to say 4. There has to be 4 newtons of strain.
Adding.
Yeah. So they're like, oh, well, there's 4 newtons. You're pulling 2 on one side and 2 on the other. If you wanted to do vernier stuff, you could actually put a force probe in here, or a force scale, which we've got over here, in there and see and have them measure. There's only 2 newtons of tension. So think of it this way. If there were 4 newtons of tension, yeah, this has got 2 newtons down, it would have 4 newtons up. This would be accelerating upward. If this had 2 newtons down, 4 newtons up, this would be accelerating upward. These things would be flying to the ceiling, which they're not doing. So now, this is actually a Newton's first law demonstration. I move it up, and now they're not even. And this is basically a massless string. It's so light. And I asked them, I'm going to let it go in a moment. What's going to happen? And they have no idea. A lot of kids will think of it like water. That, oh, Mr. Richard's going to find its level. It's going to go to here. Some kids are going to say, oh, well, it's going to start to fall, but then it's going to have speed, so it's going to keep going, and it's going to go all the way down to the floor. Some kids say it's not going to move at all. And so my point when I have it up here, and I'm tricking them because I'm holding it, is that the forces are still balanced. It's still in equilibrium. Objects without a net force want to stay at rest or move in a straight line at constant velocity. So when I let it go, what is it going to do? Nothing. And it just stays there. And it freaks them out.
Yeah.
They're like, shouldn't this fall?
Yeah.
What would I have to do to make it fall? You could give it an initial velocity, which means the forces are still balanced, so what should we see it do? Move at a nice constant speed. And it's very cool. I've read a lot of research that over and over says, because this is our habit as teachers, and I'm guilty of this all the time. You're going to make that misconception. Things don't need a force to move at a constant velocity. Don't make that misconception. That's not enough. That you need to show them something that like actually destroys it, you know, and makes them like, oh wow, I didn't understand what's going on. That's why the trick for me is I ask them to predict before I show them the demo. So when I'm here, what happens? And they tell me what they thought was going to happen, and then they're forced to recognize they were wrong, and that's big. The other way to make this thing accelerate would be to make the masses different. So you could take a small paper clip now, put it on this one, and you would see it accelerate. And I could put in 3 paper clips, and I'd see it accelerate more. And because now the tensions are not, well, the tension would be equal if we're talking about a massive string. The masses on either side, the forces would not be equal.
Now how would you